Hi there, welcome to your lesson on transformations of reciprocal functions. In a recent lesson, we looked at what happens when you transform your basic reciprocal function. In this one, we'll take a further look at that. So let's begin with, again, the reciprocal function, which looks like this. The equation is y equals 1 over x. That's our most basic form. Its graph looks like this. We have the vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Of course, last time we learned this can be moved around, and when you move it around, so do the asymptotes. Also, we know there's a domain and range. Domain is all values except for x equals 0 in this case, and the range is all y values except for y equals 0 for this one. We also know that it can change, the reciprocal function can change when you change that top number. It can be any value, and we call it the k value. All right, let's go back to our water slide situation. We have this water slide. Let's say that the reciprocal function is going to be used as a model for this water slide here. It says the floor and the wall of the swimming pool are to be modeled with the x and y axis. So for example, this y axis here is considered the wall behind the water slide, and this here is considered the water level, or the floor here, the water level. Okay, so if this was the slide here, it would begin right by the wall and then it would drop you off right by the water here. But let's say the designer wants to ensure that the slide begins away from the wall, so they want this to begin away from the wall so there's room to kind of get on the slide, and also that there is a gap between the end of the slide and the pool, so that when you're going down, there is a vertical drop into the water. So when you come down the slide, you end up falling into the water rather than just being kind of laid into the water. So how can we transform this reciprocal function to achieve these goals of moving it away from the wall and leaving a gap? Well, I hope you were thinking we can just simply do something like this. Okay, so in our last video, we looked at this. We looked at how do we translate a reciprocal function. Well, here is translation being applied to the x values. When we see x minus 4, it means it's moved 4 units right. And here we see a 3 being added to the entire function, which means we've moved it up 3 units. And we can see that transformation here. The entire reciprocal graph has been moved right 4 and up 3. So now the asymptotes are at x equals 4 and y equals 3. So this part here, which used to model our slide, has been shifted like we wanted. It's moved away from the wall, and it's moved up so that there's a drop into the water here at the end of the slide. Okay, so that's basics of translating reciprocal functions. We're going to take that a little further in this lesson. So we know there's our asymptotes. Okay, so what else do we have? So our vertical asymptote was that, remember, we find it by taking the denominator, setting it equal to 0, because when this denominator becomes 0, we have an undefined fraction, and therefore there's a hole in the graph. So we set the denominator equals 0, we solve for x. That's our vertical asymptote, x equals 4. We see it here. Okay, for our horizontal asymptote, we just said we look at this, the shift, we see it's been shifted up 3 units, therefore our horizontal asymptote is now at y equals 3. Okay, that's what we know so far. Let's take this a little bit further now. But taking that same idea in this question, we have this. Okay, so this is a very much an exam style kind of problem here. We have this function. We see our two translations there, just like we did a moment ago. We see a shift here and a shift here. And it says, show that this function is a self-inverse. So first, to remind you, a self-inverse means when you take the inverse of it, you get the same function. So try to find the inverse of this and show that it's the same function. Okay, let's check our work here. So there's the original function. The inverse, we take the x and y values and we swap them. Okay, now we're going to subtract 1 over here, so we get x minus 1. Then we can, whenever we have a fraction like this, we can multiply by y minus 1 and divide by x minus 1. So basically we can switch the positions of these two things like this. So y minus 1, x minus 1. And now we're almost done resolving it for y. Now we can just add 1 on that side, and we've solved it for y again. So this is our inverse, this is our original, and we can confirm they're the same. So this function is a self-inverse. The inverse of it is the same as the original. Okay, let's go to the next part. It says state the range of the function. Well, we might want to begin by imagining what the graph looks like, because the graph will help us figure out what the domain and range are, right? So here's the graph of it. We can see from this, when we learned before, that this x minus 1, it shifts 1 to the right, and this plus 1, it means it shifts 1 up. So you can see the graph here. It shifted 1 right and 1 up. So our horizontal asymptote is y equals 1, and our vertical asymptote is also x equals 1. So the whole graph is moved one right, one up. Okay, so that allows us to state the range. The range we know is going to be all y values except for this asymptote. So there's our range. All real numbers except for y cannot be 1. Okay, so I hope you can even do that without graphing now. Now that you know how these shifts work, you should be able to do that without thinking about the graph. Or I mean, think about the graph, but you shouldn't have to sketch it. Okay, it says sketch the graph. Well, we have the graph now. But let's take a look at something else that was given to us in the problem. We were told that x values have to be greater than 1. So in the beginning, it defined this function on this domain. It said we're only looking at this function when x values are greater than 1. So this is not actually the right graph for what we see here. We want only x greater than 1. So we want only this part of the graph, because here's x equals 1, and we want everything greater than that. So to truly graph what it says here, including this restriction, would be to graph only that part. So if we graph only that part, it looks like this. And therefore, our range of that one is not this full range. The range then is y values greater than 1. Because for this portion of the graph, the range, the y values that this graph exists on are only y values greater than this asymptote. So they're only y values greater than 1. So that's a little twist in that question. I just wanted to show you something like that. Okay, so now let's move on with our transformations. Let's say we had our basic reciprocal function and somebody said translate it 2 units up. Well, the function would look like this, right? We add 2 to the entire function. So we know that will move the whole thing up 2 units. And now, there's our graph, right? Here's the y asymptote at y equals 2. The whole graph has moved up 2 units. Okay, but now let's do something else with that. So first of all, our vertical asymptote, we know we take that thing, the denominator, set it equals 0. So that's our vertical asymptote. Our horizontal asymptote we know is 2. It's that shift. The shift tells us where our horizontal asymptote is. But now let's do something different. Let's say we were told to change this function to a form that looks like this. Notice this is all written as one fraction, whereas here we have a fraction plus a number. So our goal, in other words, is to combine this fraction and this number into a single fraction. So here's how we can go about doing that. Here's our original function. We're going to multiply the second piece by x over x. X over x is just 1, so we're not actually changing anything. If we say 2 times 1, because that's what this is, we're not actually changing it. We're changing what it looks like, but we're not changing what it is. So we're multiplying by x over x because we want to have a common denominator of x. So that gives us this, 1 over x plus 2x over x. Now that these have a common denominator, we can combine the numerators to add the fractions. And we know when we add fractions, the denominator stays the same, like this, but we can just add the numerators, so 2x plus 1. So there, we've taken that function, changed it into a form that looks like this. So in other words, if you graph this or graph this, it should give you the same thing because they're equivalent, just different forms. Okay, so now look at the horizontal asymptote. We know the horizontal asymptote was the 2 because we shifted the whole thing up 2 units. But now looking at this, where's the 2? The 2 is right here. So that number there tells us what the horizontal asymptote will be when we see this form. Okay, so either we see the shift on the y-axis here, and that tells us the horizontal asymptote, or we see it in one fraction and we look at that first number there. Okay, let's look at it back to the swimming pool problem. We have the slide. We created this model. We know our vertical asymptote, x minus 4, set it equals 0, x equals 4. There's our vertical asymptote. Our horizontal asymptote is that number there, the 3. All right, so our horizontal asymptote is 3. That's the way we looked at it before. But let's take this one now and change the form as well. So can we change this one to this form? So try it now. Okay, in this case, we have our original. We're trying to make a common denominator again, so we multiply this 3 here by x minus 4 over x minus 4, which is just 1. Okay, when you multiply that, you get this, 3x minus 12 for the second part, and then now they have a common denominator, so now you can combine the numerators to get 3x minus 11, because this is like 3x minus 12 plus 1, and that. So now again, if you graph this one or this one, it would give you the same exact graph. And now let's look at the horizontal asymptote again, because the vertical asymptote remains the same. We know it's x minus 4, set it equal to 0, and we get x equals 4. But what about the horizontal asymptote? So again, here we see the 3, so we know that's horizontal asymptote. Here we see the 3 in front here, so that's our horizontal asymptote. Okay, I think we're seeing a pattern. That number in front tells us the horizontal asymptote. Perhaps. Let's take a look at one more. So here's another function, and let's say if let's find the vertical asymptote of this one. Okay, there we have it. We set the denominator equal to 0, and we solve that, we get -3/2. How about the horizontal asymptote? Well, it's y equals 4, this number here. We see the shift, the vertical shift right here. Now let's change the form and see what happens. Well, here's the graph first of all, sorry. We have y equals 4 here, and then we have x equals -3/2, which is -1.5. We can see right here. So there's our graph. Now let's try to change the form of this one as well. Let's see what we get. Okay, so try this one out. Okay, changing the form, take the second number, multiply by 2x plus 3, because that's the number, sorry, the denominator there. We're going to make a common denominator. Multiply this, we get 8x plus 12. Combine those fractions now, we get 8x plus 13. So there's our changed form. Now, we learned that this number here is our horizontal asymptote. We see 4 and 4. But now, in the previous example, we would look at that number and say, hey, that's our horizontal asymptote. But this time it doesn't work. I see an 8 here, but we know our horizontal asymptote is 4. So can you see another way to get the 4? Okay, hopefully you're looking at both of these numbers here now, 8 and 2, and you see, oh, 8 divided by 2 gives us 4, and that gives us a horizontal asymptote. So we've come to a very important conclusion that this number divided by this one gives us our horizontal asymptote. In the last situation, let's go back for a moment, we had this. Well, we can think of it the same way. We could have done 3 divided by 1, because there's a 1 here, and we get our horizontal asymptote. So always this number divided by this one, the two coefficients of x. Okay, let's pause there one more time just so you soak that idea in. To get our horizontal asymptote, we divide the two coefficients of x when we have a single fraction like that. And our vertical asymptote, we just look at the bottom and set equals 0. Okay, let's summarize that. So when we have a function of this form, our vertical asymptote is just denominator set equal to 0. So in this case would be -d over c. In this form here, oh no, let's look at horizontal. Horizontal asymptote, oh no, I did go here. Okay, so our vertical asymptote here would be the same thing. Denominator set equal to 0, same thing. So whether the fraction is like this or like this, both functions we can find the vertical asymptote the same way. But horizontal, here, this tells us the horizontal asymptote, y equals q. Whereas in this form, when we don't have a number added here, we look at the coefficients a and c, and that's our horizontal asymptote, a divided by c. So try this one here, vertical and horizontal asymptotes, and now check your work. Here's your vertical asymptote, here's your horizontal asymptote, that number there. How about this one here? Okay, vertical asymptote is that, set the denominator equals 0, and horizontal asymptote is this number divided by this one, which is 1/2. Great. So the general steps for graphing a rational function, that's where we've come to, is to find the vertical asymptote, find the horizontal, and then find the x and y intercepts. We know when we want the y-intercept, we make x 0, and when we want the x-intercept, we make y 0. So let's try that here. So here we're going to find the vertical asymptote, 2x minus 6 equals 0. Horizontal asymptote is 4 divided by 2, which is 2. And then x-intercept, we set y equal to 0, solve that. When we have 0 here, we can multiply by this 2x minus 6, and it cancels it away. We're left with this. Solve that, we get -1/4. That's our x-intercept. Our y-intercept, we make x equal to 0. So you make both of these x's here 0. Those both become 0. You end up with 1 over -6, which is -1/6. Now that you have the asymptotes and these two intercepts, it's enough to graph it. So you do have enough to graph it now. To graph, we can begin with the asymptotes. So you can draw your asymptotes in, you know where they are, x equals 3, y equals 2, draw them as dotted lines, and now you have to decide, are the curves going to be here and here, or are the two curves going to be here and here? And since we have these x-intercepts and y-intercepts here, we know one curve will definitely be here, so that means the other curve will be here. So our graph looks like this. And in this case, I know the x and y-intercepts were very close to the origin there, but anyway, they are still important in telling us where these two curves should be, and they give us an idea of what they look like. So there's our rational function graphed. Try the same thing. Oh, there's our domain and range as well. We know domain is all real numbers except for 3, and range also all real numbers except for 2. Try the same thing with this one. And now check your work very carefully and make sure you got this all right.